Time, as we experience it, flows in one direction, forward. From the past through the present to the future. This is the natural order of things. We see this in our everyday lives. A cup falls and shatters, never the reverse. We age as time marches on. This unidirectional flow of time is often referred to as time's arrow. It's a concept deeply ingrained in our understanding of the universe. However, the question of whether time can flow backward into the negative has captivated physicists and philosophers for centuries. The very notion of negative time challenges our fundamental assumptions about reality. Could there be a realm where time runs backward, where effects precede causes? Exploring this mind-boggling possibility takes us to the frontiers of theoretical physics. The concept of negative time arises from the equations of theoretical physics. Just as mathematical equations allow for negative numbers, certain physics equations don't preclude the possibility of time flowing in reverse. This doesn't necessarily mean negative time exists, but it does open up a fascinating avenue of exploration. Imagine a universe where time flows backward. People would grow younger instead of older. Memories would be of the future, not the past. The shattered cup would reassemble itself. As bizarre as it sounds, this is the kind of scenario that negative time presents. The implications of such a reality are profound. It would challenge our very understanding of cause and effect, history, and even free will. While still largely theoretical, the pursuit of negative time could revolutionize our comprehension of the cosmos. To grasp negative time, we must first understand how physicists conceptualize time. In classical physics, time was seen as absolute and unchanging, a universal metronome ticking away at a constant rate. However, Einstein's theory of relativity revolutionized our understanding. Relativity posits that time is not absolute, but relative, dependent on the observer's frame of reference. Time slows down in stronger gravitational fields and at speeds approaching the speed of light. This concept, known as time dilation, is experimentally verified. Negative time in this context doesn't necessarily mean going back to relive the past. Instead, it suggests the possibility of time having a negative value in certain frames of reference or under specific conditions. This is where the realm of quantum mechanics, the study of the very small, comes into play. Section 4. The theoretical framework, from relativity to quantum mechanics. In this section, we delve into the fascinating transition from the deterministic world of relativity to the probabilistic realm of quantum mechanics. This shift not only revolutionized our understanding of the universe, but also introduced concepts that challenge our very perception of reality. Quantum mechanics, with its probabilistic nature, introduces even stranger possibilities regarding time. Unlike classical physics, where events unfold in a predictable manner, quantum mechanics suggests that, at the smallest scales, the universe operates in a fundamentally different way. This has profound implications for our understanding of time and space. Particles at the quantum level don't follow the same rules as objects in our macroscopic world. They behave in ways that seem counterintuitive, often defying our everyday experiences. For instance, a particle can be in multiple places at once, or it can appear and disappear seemingly at random. This unpredictability is a cornerstone of quantum theory. They can exist in multiple states simultaneously, known as superposition, which means a particle can be in a combination of states until it is observed. This phenomenon is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box can be both alive and dead until someone opens the box and observes it, and can even tunnel through seemingly impenetrable barriers. This is known as quantum tunneling, where particles pass through barriers that would be insurmountable according to classical physics. This effect is not just theoretical, it has practical applications in technologies like semiconductors and tunnel diodes. Some interpretations of quantum mechanics suggest that time itself might be quantized, meaning it exists in discrete packets rather than flowing continuously. This idea challenges the traditional view of time as a smooth, unbroken continuum and opens up new avenues for understanding the fabric of reality, meaning it exists in discrete packets rather than flowing continuously. If time is quantized, it could fundamentally alter our understanding of causality and the sequence of events. This concept is still highly theoretical, but it has the potential to revolutionize our understanding of the universe. If time is quantized, it opens up the possibility of negative time quanta, which would be analogous to negative charges in electricity. This means that just as we have positive and negative charges, we could have positive and negative packets of time. This idea is still speculative, but it offers intriguing possibilities for the nature of time. Analogous to negative charges in electricity, the concept of negative time quanta could lead to new insights into the symmetry and structure of the universe. It challenges our conventional understanding and invites us to think about time in entirely new ways. Another intriguing concept is that of time symmetry. Time symmetry suggests that the fundamental laws of physics are the same, whether time moves forward or backward. This idea is deeply rooted in the principles of physics and has far-reaching implications for our understanding of the universe. Many fundamental laws of physics, like those governing electromagnetism and gravity, are time-symmetric. This means that these laws do not change if the direction of time is reversed. The symmetry is a fundamental aspect of the universe and has been confirmed by numerous experiments and observations. This means they would work the same way if time ran backward. The idea of time running backward is not just a theoretical curiosity. It has practical implications for understanding the nature of time and the universe. It suggests that the past and future are not as distinct as we might think. This symmetry has led some physicists to speculate that negative time might be just as valid as positive time. If true, this would mean that time could flow in both directions, opening up new possibilities for understanding the nature of time and the universe. This idea is still highly speculative, but it offers a fascinating glimpse into the potential future of physics. Section 5. Echoes in the cosmic microwave background. One area of active research where negative time might play a role is in cosmology, the study of the origin and evolution of the universe. Cosmology seeks to understand the grand narrative of the cosmos, from its earliest moments to its ultimate fate. This field encompasses a wide range of phenomena, from the birth of stars and galaxies to the mysterious dark matter and dark energy that seem to dominate the universe. The prevailing model for the universe's beginning is the Big Bang theory. This theory posits that the universe began as a singularity, a point of infinite density and temperature, approximately 13.8 billion years ago. From this singularity, the universe has been expanding and cooling, leading to the formation of the complex structures we observe today. The Big Bang theory describes the universe starting from an extremely hot, dense state and expanding over time. As the universe expanded, it cooled, allowing particles to form atoms, which eventually led to the creation of stars, galaxies, and all the cosmic structures we see. This expansion continues today, with galaxies moving away from each other, a phenomenon known as cosmic inflation. Evidence for this theory comes from the redshift of distant galaxies and the cosmic microwave background radiation, a faint afterglow of the Big Bang. The redshift indicates that galaxies are moving away from us, supporting the idea of an expanding universe. The cosmic microwave background radiation, discovered in 1965, provides a snapshot of the universe when it was just 380,000 years old, offering crucial insights into its early conditions. Some physicists have proposed that the Big Bang might not have been the absolute beginning. Instead, it could be a transition from a previous state of the universe. These alternative theories suggest that the universe undergoes cycles of expansion and contraction, known as the Big Bounce. Instead, our universe could be part of a larger multiverse, where universes are born and die in a potentially infinite cycle. In this multiverse scenario, each universe could have different physical laws and constants, leading to a vast and diverse cosmic landscape. The idea of a multiverse challenges our understanding of reality and opens up new possibilities for the nature of existence. Negative time could be a factor in these cyclical models. In such models, time might not be a linear progression from past to future, but could instead have a more complex structure, with time running backward in certain phases of the universe's cycle. This concept of negative time is still highly speculative, but it offers intriguing possibilities for understanding the nature of time and the universe. Section 6. Negative time and the creation of the universe. In these cyclical models, the universe expands for a period, then contracts, eventually collapsing in on itself in a big crunch. This cyclical nature suggests that the universe is not a one-time event, but rather a continuous process of birth, death, and rebirth. The expansion phase is characterized by galaxies moving away from each other, stars forming, and cosmic structures evolving over billions of years. This crunch could then lead to another Big Bang, creating a new universe. The concept of a new universe emerging from the remnants of the old one is both fascinating and mind-boggling. It implies that the end of one universe is not the end of everything, but rather the beginning of something entirely new. This cycle of Big Bangs and Big Crunches could have been happening for an infinite amount of time, with each cycle giving rise to new cosmic structures and phenomena. Negative time could come into play during the contraction phase. As the universe begins to contract, the conventional understanding of time as a linear progression from past to future might no longer apply. Instead, time could start to behave in ways that are completely alien to our everyday experiences. As the universe contracts, time might not simply run backward as we conventionally understand it. The idea of time running backward is intriguing, but negative time suggests something even more complex. It could mean that events unfold in a manner that defies our current understanding of causality and sequence. Instead, it could take on a negative value, representing a reversal of the arrow of time. This reversal would not just be a simple rewinding of events, but a fundamental change in the nature of time itself. Negative time could imply that the future influences the past, creating a loop where cause and effect are intertwined in ways we can't yet fully comprehend. This reversal would have profound implications for the laws of physics and the behavior of matter and energy. If time can take on negative values, the fundamental forces that govern the universe might operate differently. Matter and energy could behave in ways that are currently unimaginable, leading to new forms of cosmic phenomena and possibly even new types of particles and forces. While still highly speculative, the idea of negative time playing a role in the creation and destruction of universes offers a tantalizing glimpse into the potential vastness and strangeness of the cosmos. It challenges our understanding of reality and opens up new avenues for scientific exploration. The concept of negative time invites us to rethink the very nature of existence and the universe, pushing the boundaries of what we consider possible.